This video is intended to assist pilots in applying weather theory to their flight operations. Density altitude is the altitude in the standard atmosphere that has the same density as the location of the aircraft. Well, that's easy for me to say. Density altitude is affected by air temperature, atmospheric pressure, elevation, and to a small degree moisture. Of these, temperature and elevation are the most significant factors. All aircraft are affected by density altitude and have performance limitations. And although turbocharged and turbine engines provide increased power, rotor, propeller, and wing efficiency decrease with higher density altitude. All pilots must understand their aircraft and not attempt to exceed the aircraft's design performance. This is especially true for low-performance, multi-engine airplanes, where single-engine ceiling may be lower than the airport's density altitude.
We all have to learn from the mistakes of others, because we won't live long enough to make them all ourselves. During this video, we'll review various case studies. When we discuss accidents and incidents, let's concede that hindsight is always 20/20. It's easy to sit back and analyze and criticize someone else. Examples are not intended to disparage or malign any individual, group, or organization. Their sole purpose is illustration. Our goal is prevention through education.
Calculating aircraft performance is extremely important and a requirement for every flight. Most density altitude accidents involved improper takeoff procedures. In nearly half, the pilot attempted takeoff in excess of maximum gross weight. About 1/3 attempted to exceed the climb performance of the aircraft. Just as with takeoff and climb performance, landings are affected by density altitude. POH performance numbers typically reflect the shortest distance we will ever be able to take off or land our airplane. There are no requirements for any margins in the published data. They are generated by skilled test pilots in nearly perfect conditions. Techniques that you or I would use to show off our flying skills will typically add tens, if not hundreds of feet to the published performance data. The following incident, which took place at an airport near sea level, illustrates these points.
The NTSB determined the probable cause as the pilot's inadequate planning, preparation, and takeoff technique. 4 pilots were planning to fly to an aviation safety seminar in a Piper Arrow.
Anyone care to guess what certificates these pilots held? Yes, certificate. The FAA can't spell license.
An investigation revealed the airplane was about 175 pounds over maximum takeoff weight, density altitude was 4,500 feet, and the runway had a 0.5% upslope grade. For an obstacle clearance takeoff, the pilot's operating handbook recommends a 25-degree flap setting with full power before brake release. Flaps were set to 10 degrees and full power was applied utilizing a rolling takeoff. The pilot rotated near the end of the 3,000-foot strip. The airplane climbed to about 40 feet before settling into the trees.
You guessed it, all were flight instructors. The information required to calculate aircraft performance consists of airport, weather, and aircraft data. Airport data can be obtained from charts or the airport facility directory. Weather data from airport sources, such as automated weather observations, the airport control tower, or Unicom, or pilot observations from wind cones, wind tees, or tetrahedrons, and aircraft data from the pilot's operating handbook. Pilots from coastal areas, plains, and valleys may have little if any experience with mountain flying or high-density altitude operations. Frequently, their first experience follows this scenario. They depart their home airport, fly over mountains, often at the limit of the aircraft's performance, and land at a high-density altitude airport. On departure, they not only have to contend with a high-density altitude takeoff, but with significantly reduced climb performance. Pilots en route are not immune from aircraft performance limitations. An aircraft service ceiling is based on standard conditions. A run-out engine, poor leaning technique, over gross weight, and turbulence and downdrafts would further decrease aircraft performance. Some have mused that one could walk across the Rockies and Sierra Nevadas on the wreckage of Cessna 172s and Piper Warriors. You can't fool Mother Nature. Winds and temperatures aloft forecasts can be used to determine density, altitude, en route. On warm summer days, it's not unusual for density altitude to be 1,000 feet or more higher than indicated altitude. This may not seem like much, but when you're operating near the limit of the aircraft's performance, it can be critical. Additionally, if the aircraft is within 2,000 feet of the surface, especially during the afternoon, surface heating through conduction can cause the air temperature aloft to be significantly higher than forecast. In this example, and it's only mid-May, temperatures aloft are already considerably higher than standard. The average temperature between Phoenix and Tucson at 6,000 feet is plus 20 degrees Celsius. Density altitude 8,000 feet. At 9,000 feet for western Arizona, the average density altitude is 11,000 feet, and at an altitude of 12,000 feet, density altitude is almost 13,500 feet. Lower than standard pressure and high humidity would further increase density altitude. Take, for example, this case study.
The NTSB determined the probable cause was the pilot's failure to maintain airspeed, which resulted in a stall, and the decision to conduct flight beyond the aircraft's performance capability. Two pilots, returning from the West Coast in a Cessna 172, were attempting to cross the Continental Divide where the elevation is 11,530 feet. Density altitude was calculated to be 14,300 feet. The airplane's VOH lists the service ceiling as 13,000 feet. A witness reported the airplane appeared to be stationary, banked hard right, and went straight down.
Winds across mountain peaks in excess of 25 knots imply possible moderate turbulence. In excess of 40 knots, moderate or greater turbulence. Due to Venturi effect, winds through passes and canyons may significantly exceed winds aloft forecasts. This is why the FAA recommends, to avoid the most significant turbulence, climb to an altitude 3,000 to 5,000 feet above mountain tops before crossing. In the west, that's 13,000 to 19,000 feet. Not possible for many aircraft. Often, the only practical solution is to avoid areas of winds greater than 25 knots, fly over lower terrain, or accept the consequences. If terrain on the other side of the ridge is getting higher, you've cleared the ridge. If not, you haven't. Expect updrafts on windward slopes and downdrafts on leeward slopes. Approach ridges at a 45-degree angle. If you're unable to clear the ridge, this will allow a faster retreat to lower terrain. Expect the highest and most critical density altitude between early afternoon until shortly before sunset, when temperatures are highest. To avoid the most critical conditions, plan flights during the early morning or evening hours. Many websites, including those of the National Weather Service, provide maximum temperature forecasts. These can be used to determine approximate density altitude during initial pre-flight planning. Runway gradient refers to the slope of a runway. Gradient is published in the Airport Facility Directory for those airports with an FAA-approved instrument approach procedure. Slope is shown when 0.3% or greater. For example, at Columbia, California, runway 1735 has a 1.1% upgrade toward the north. Rule of thumb: increase takeoff distance by 10% for a 2% upgrade. Increase landing distance by 10% for a 2% downgrade. Approaching Columbia, California, we monitor the AWOS for airport conditions.
Columbia Airport, automated weather observation. Wind 190 at 5. Temperature 39 Celsius. Altimeter 290 4. Density altitude 5. 1,300.
Columbia has an elevation of 2,118 feet. We'll use runway 17 with 4,075 feet available for landing and a 1.1% downgrade. In the warm season, even with a field elevation of only around 2,000 feet, density altitude can occasionally exceed 5,000. Aircraft performance is calculated using a graph or table. For a detailed explanation of calculating wind components, pressure altitude, and table interpolation techniques, refer to the National Weather Association's Weather Theory for Pilots program, Aircraft Performance. Enter the table at the 2,000-foot pressure altitude row. Move right to the 40°C column and read the landing distance over a 50-foot obstacle of 1,405 feet. We'll add 10% for the downslope grade, just to be on the safe side. This results in a landing distance of 1,545 feet, certainly safe for our operations under the given conditions. As well as runway overruns due to density altitude, poor pilot technique contributes to landing accidents. Avoid a high approach. Regardless of density altitude, fly the same indicated airspeed you would at sea level. Leave the mixture lean based on the calculated density altitude as recommended by the POH to provide for smooth engine operation, especially in the case of a go-around, and to prevent engine stoppage on landing due to an over-rich mixture. Prior to departure, we monitor AWOS to determine airport conditions and calculate takeoff and initial climb performance. The AWOS reports wind 190 degrees at 5 knots, temperature 39er, and the altimeter 294. Our airplane's weight is 2,200 pounds. Begin at 39 degrees on the temperature scale and proceed vertically to the pressure altitude value of 2,000 feet. Move horizontally to the airplane weight reference line. Proceed parallel with the diagonal reference lines to the weight value of 2,200 pounds. Then horizontally to the wind reference line. Move parallel with the blue diagonal reference lines to the headwind value of 5 knots. Continue horizontally and read the obstacle clearance takeoff distance of approximately 2,200 feet on the right vertical scale. Initial climb performance is as important as takeoff calculations for high-density altitude operations. It doesn't make any sense to claw yourself into the air and not be able to climb out of ground effect or over adjacent terrain. Locate 39 degrees on the temperature scale and proceed vertically to the pressure altitude value of 3,000 feet, 1,000 feet AGL. Proceed horizontally to the airplane rate of climb reference line. Move down and read 425 feet per minute on the bottom horizontal scale. Based on these calculations, departure and initial climb under given conditions are within the aircraft's performance capability. How much of an issue is moisture on air density? Since moisture is not factored into performance calculations, and there are no general rules of thumb, it would not seem to be a significant parameter. And in fact, in most cases it isn't. Typically, moisture has less than a 2% effect on airplane performance. Under extreme cases of high temperature and high humidity, the factor may increase to almost 8%. Operationally, if we round up our performance calculations, under most conditions we'll take care of the moisture factor. Certainly, if you're operating in an airport with high temperature and high humidity, you may wish to add an additional 10% cushion to your performance calculations. Like landing performance, takeoff distances are conducted by skilled test pilots with an airplane in prime condition. A run-out engine and poor leaning or pilot technique would add additional distance. Experiment with the airplanes you fly. Determine the actual takeoff and landing distance, then compare them with booked values. Operationally, have enough runway to allow a safe landing if the airplane cannot climb out of ground effect. This requires calculating both takeoff and landing distance over a 50-foot obstacle under existing conditions. If the sum of these distances, including at least a 10% margin, is less than the runway length, the risk may be too great. With a calculated takeoff distance to clear a 50-foot obstacle of 2,200 feet, add our landing distance of 1,545 feet. To this value, add a 10% margin. This results in a balanced field length of approximately 4,200 feet. With 4,670 feet available for takeoff, we are within our personal operational limits. Select a point based on calculations where the aircraft will be out of ground effect with a positive rate of climb. If not, this point will allow us to abort the takeoff and land on the remaining runway. Lean the engine as prescribed by the POH. Use all available runway. If you're flying a non-turbocharged airplane with a constant speed propeller, expect maximum manifold pressure to be 1 inch less per 1,000 feet of density altitude. Out of ground effect with a positive rate of climb prior to the abort point, continue the takeoff. If possible, remain in the pattern to ensure adequate climb performance. If the performance isn't there, hopefully you can make a safe landing back at the airport. Consider general weather conditions and route of flight. A successful takeoff and initial climb can be ruined if the airplane cannot clear surrounding mountains. This may be hampered by high terrain, high density altitude, downdrafts, and wind shear. With an airplane approaching the limits of its performance, any or all of these conditions would strongly indicate a no-go decision. There is no additional danger in high-density altitude operations as long as we calculate and do not attempt to exceed the aircraft's design performance or fly beyond our own personal training and experience levels. Recall the sage axiom: aviation in itself is not inherently dangerous, but to an even greater degree than the sea, it is terribly unforgiving of any carelessness, incapacity, or neglect. An experienced commercial pilot was ferrying this airplane from the Midwest to California during the warm season. The pilot lost control at 8,500 feet MSL west of Rock Springs, Wyoming. Density altitude was calculated to be over 12,000 feet.